Hello, my name is Sataka Furui, Tokyo University, and I'm a user of Mathematica since 1990 or so, but I'm not so accustomed to the progress of Wolfram language. But I would like to speak about fractional calculus, Langevin equation, and quaternion used in Mathematica. This is my abstract. In analysis of nonlinear differential equations, fractional order calculus attracting interest of researchers. Langevin equation is a stochastic differential equation, and it can be reduced to Ito's stochastic differential equation. We take a specific linear process and obtain the Fokker-Planck equation, which can be regarded as half-order fractional differential equation. There are several fractional order differential equations. We consider the Caputo fractional differential with initial conditions and with boundary conditions. The left derivative and the right derivative can be calculated by Mathematica, and they are different for the case of fx equal x minus a to the nq's order and b minus x to the nq order. X runs from a to b, and where q is not integer. In fractional differential equation, complex variables can be extended to quaternions and biquaternion variables. In analysis of 2 plus 1 dimensional ultrasonic wave spectra, a solution of quaternion differential equation reproduces the conformality of the spectra. And in analysis of 3 plus 1 dimensional ultrasonic wave propagation, homologous space-like time-based split quaternion can be used for the fixed point action lattice simulation. The Langevin equation I have done in 1997 with Professor Nakajima, and on the Langevin equation is shown in this kind of differential equation. And eta, this bracket is averaging over the product of Gaussian distribution and the solution of the equal stochastic differential equation. We introduced a parameter s equals square root of t, and where t is the time, and u to the ith is kx to the I, obtain the corresponding Fokker-Planck equation, p tk eta, where the Fokker-Planck equation p tk eta has 3 dimensions and satisfies derivative of pi by t gives the second order derivative of pi by x, and first order derivative of kx pi. And the Fokker-Planck equation can be solved exactly in the case of ux equal to minus kx. We introduced the parameter alpha tk, this one, and we choose k equal 1/2 and alpha tk t 1/2 equal to 1 minus e to the minus 1. And so alpha taken like this one, and if I plot it, it shows this curve. The initial condition is taken to the x0 called x01, and then solution of x1t pi turns this equation. We check the Fokker-Planck equation by calculating the left-hand side and right-hand side. So left-hand side is derivative of by t, and this is this function of t and x. So this is the three-dimensional plot of the function solution. And the right-hand side has two parts. And the first part is second-order derivative of P1. P1, P2, P3 are all the same in our case. So, and this is a second order. This is a second part. And if make a sum of these two, it should be equal to left-hand side. So I check the two terms, sum of the two minus left-hand side, and then I find that this is completely zero. So P2 and P3 also satisfy this equation, and the solution of the Fock-Kaplan equation is verified. And for to study in the Brownian step or Brownian motion, we Brownian step S equals square root of t, and take t is time. The Langevin equation is the fractional order differential equation. The Riemann-Liouville integral can be calculated by mathematical. And in the flat 3D space, the Langevin equation is written in this form, and you have the solution has three terms. The first one, x1, it is function of s, eta 1, eta 2, eta 3, and u1, u2, u3. And this is x2, and this is x3. Then we check the symmetry of the wave function. So simplify x3 minus x2, and x3 minus x1, and x2 minus x1, and you can check the symmetries. So Caputo fractional integral, and about 2 years ago, last year, Kiskinov et al. Discussed whether the left side and the right side Caputo fractional derivative, that is written in here, these two should be equal, as written by Vatsara et al. In 22 for continuous function fx. He considered the integral of fx equal s to the 0.25 and 1 minus s to the 0.25. The former is 1 over gamma function of variable 0.75 times the following integral. And that integral can be calculated by mathematical. And we choose t equal to 0.2 and obtained it's 1.03457 over gamma 0.75. This is the 0.84426. It is the same as the Kiskinov has shown. And the latter is the gamma 0.1 over gamma 0.75 times the following integral, and integrate this one. And there appears a condition, and this is very complicated. So I replace final one, boundary value to b, and then I obtain this expression, and then choosing b equal 1, I obtain this result. And this is gives 0.495808, and it's the same as the Kirchner et al., except the sign. That is the Kirchner. I think the Kirchner et al. Missed factor -1. And the Gegenbauer polynomials and the Langevin equation is a well-known fractional differential equation. And Elgingi and Kirefat proposed to solve the equation using the Gegenbauer polynomials. Mathematica has Gegenbauer C that satisfies this differential equation. The polynomial is real-valued orthogonal function with respect to the weight function given in this form. And orthogonality of Gegenbauer polynomial can be checked by using dot command, which is to integrate conjugate of f and g and the weight function square root of 1 minus x squared, and the integral from -1 to 1. And orthogonality command 1 to x to the 6 dot command gives this table, and the polynomial agree with the Gegenbauer C, which is exists in Mathematica, and table Gegenbauer C gives the same polynomials. Using the expression xx1 square root of t eta 1 k kx1 obtained from previous x1, I define x1 this equation, and choosing eta 1 equals 0.2 and k equals 0.5, I obtained this equation, and this is the sixth order polynomials, but each term can be expanded by the Gegenbauer polynomials. That, for example, this t is t to the 6, and this is the first. This is a constant. This is okay. The last one term can be expanded by constant, then the second order term, and fourth order term, and the sixth order term. So Elgingi transformed the parameter t to t minus tau equal t y to the 1 over alpha, and considered the branching cut by a function z equal w e to the w, and we reduce e to the u plus 1 times u plus 1 equal to 1 to e over 2, and we obtain the solution u equals -1 plus product log 1 over e over 2, and the product of 0 e over 2 minus 1 equal to minus 0.314923, and Elgingi considered Gegenbauer polynomials of real variables x, but we consider the complex z, and this is Mathematica shows that the Gegenbauer C of 5.z is this form, and this is a real part, and this is imaginary part of C. And the differential equation, quaternion, is an extension of complex number expressed as q equal q0 plus q1i plus q2j plus q3k, and ij is minus ji equal to k, jk equal kj equal to I, and ki equal minus ik equal j, and ii equal jj equal kk equal ijk equal -1. The dynamics of 2 plus 1 dimensional space can be expressed by quaternions But 3 plus 1 dimension dynamics, we need biquaternions or split quaternions. And biquaternion function is proposed by Dirac, and he studied Lorentz transformation of biquaternions and expressed quaternion as the ratio of U to V, and assigned Q1 equals UV bar, where UV bar is the conjugate of V, and Q2 equals UU bar, and Q3 equals VV bar. Mathematical basis of quaternions has studied by non-commutative geometry, and also by Wolfram non-commutative differential calculus. The function product log that appears in the Gegenbauer polynomials calculation has a branch cut on the complex plane from minus 1 over e to e minus infinity. This is in this one. And when u is replaced by v, q1 changes to q3 prime, and q3 changes to q1 prime, and q2 changes to u bar v, which can be assigned as a branch of q2 prime. And when the v bar is replaced by u bar, q1 changes to q2 prime, and q2 change q2 double prime, and q2 changes to q1 double prime, q3 changes to q1 bar equal to v u bar, which can be assigned as a branch of q3 double prime. And replacement of do not change the elements of quaternions, and only the branch lines changes from to minus omega over e, or minus omega square over e. And the split quaternion, the Gold-Perashvili defined the split quaternions in this form, Q0. This is a Q2 plus Q3i times j. So let's combine these two. And the conjugate is defined in this form. And we consider also the Q0 equals Q2j plus Q3 plus Q1j times k, and also Q0 plus Q3k plus this form. And the fact that ij equal k can be taken as that in 2 plus 1 dimensional case, the k is taken as a time, and so conformal O2-1 symmetry can be expressed by quaternions. And time reversal based nonlinear elastic wave spectroscopy, which is done by Dr. Dos Santos in France, experiments confirm the conformality of 2 plus 1 dimensional spectra. And space-like time-based quaternions. Then Tomonaga proposed Lorentz covariant dynamics using space-like time. In the propagation of ultrasonic wave in 2-dimensional, we consider paths of the fixed point action of lattice QCD adopted by Dugrand et al., and restricting the length of the path to be less than or equal to 8 lattice units in one direction. Then there are 7 paths which contain time delay defined by the space-like time. We place wild fermions on the lattice sites and find the weight function of the 7 paths, which can yield minimum action using the machine learning techniques. Since 1 plus omega square equals 0, chaos plays an important role in spectra of 3-quantum dimension. The action depends on chirality of paths by comparison of experimental spectra and simulation results. One may be able to verify the chiral symmetry of the ultrasonic wave propagation. And this is the 7 paths of the 3-dimensional ultrasonic wave propagation. There are 7 This is the right-hand side shows the diagram, and the path starts from the center, and it goes from to the right, and then up, and then there the ball at the ball there exists a time delay, and it goes in this way, and then go this way, and okay, there are 7 type of paths, and we optimize the weight function of these 7 paths by machine learning techniques. And after 3,000 cycle and the 4,000 cycle, they are almost stable. And if the path in one way goes to return to the center, the path, the action becomes 0. So if this is a so I shift the 8th to the 16th path by 0.5, and then we get this smooth curve of the action. So to summarize, Langevin equation of quaternion Ornstein-Uhlenbeck process is a fractional differential equation, and the Fokker-Planck equation for this process gives a probability distribution following the Ito's stochastic differential equation. Hysteresis effects can be formulated from this equation, and the Caputo fractional differential equation has the left differential and the right differential, and which are not the same in general. Mathematical calculates the two properly. The Eigenbauer polynomials has a branch cut in a complex plane. The split quaternions and Dirac quaternions representation by U by V bar suggest that there are additional 3 quaternions, Q1 prime, Q2 prime, Q3 prime, and Q1 double prime, Q2 double prime, Q3 double prime on extended complex planes, which have the new type of triviality. In 2+1 dimensional ultrasonic wave spectra observed in the time reversal based nonlinear electric wave spectroscopy showed conformality, which can be reproduced by quaternions. And in 3+1 dimensional ultrasonic wave propagation, lattice method using split quaternions has the searching the weight function of paths on a coarse lattice by machine learning technique is promising. And for medical applications, fast optimization techniques are necessary. So this is my talk. Thank you very much for your attention. This is the references. Are there any questions?
There's one question for you.
Yes.
What was the reason behind the difference in the number sign between the value you got for the Caputo equation and the one published in 2022?
Excuse me. The 2022,
Yes.
This is the okay. The paper by the okay. I think this is a there was a mistake in the Vassara et al. And Kiskinov et al. Is correct. That is I checked that the Kiskinov et al. Has the correct answer, except for one sign that Mathematica gives that the correct calculations results.
And they also said very nice talk.
Yeah, but I think that the function, the choice of function is maybe crucial. That is, Skinov et al. Calculated, used the function s to the 0.25 and 1 minus s to the 0.25. So, but Bassara et al. Should taken only one type of the 1 minus s to the 0.25 or something like that. So that I think due to the choice of the wave function, that is so we must be careful that which kind of continuous function is used in the calculations. Actually, Bassara et al. Showed another wrote another paper last year, this year maybe. That but they have chosen very simple wave function, and not they did not mention Kiskinov's work, and I asked them mail. I sent mail, but I did not get answer yet.